This video is an overview of the steps taken in preparing tissue samples for electron microscopy. The light microscope uses light as its source of radiation. Through a series of glass lenses, the light produces a magnified image of the specimen. This is a photograph of the kidney, taken at 1,000 times magnification using a light microscope. This is the maximum useful magnification achievable with this system. Cells of different shapes and sizes can be seen, but little cellular detail is visible. The transmission electron microscope is capable of much greater magnification, up to 1 million times, and has a resolving power approximately 200 times greater than the light microscope. The square on the photograph shows a similar area viewed with the electron microscope with a magnification of 10,000 times. The improved resolution is achieved by using a high-velocity beam of electrons to produce the image instead of light rays. At the top of a tall, evacuated column is an electron gun that sends a beam of electrons through the specimen. Electrons pass through the specimen and are focused onto a fluorescent screen by using electromagnetic lenses. When electrons impinge on the screen, secondary light rays are emitted and form an image. The resulting image is seen through a window at the bottom of the column. Alternatively, the image can be digitized and viewed on a monitor. There is a well-defined series of steps in preparing biological specimens for electron microscopy. These are fixation, dehydration, embedding, sectioning, and staining. Fixation is the first step in tissue preparation. It stabilizes the cellular organization. Cellular structure is best preserved if fixation occurs as close as possible to cell death. Tissue samples are cut into small pieces of about a cubic millimeter before being immersed in the fixative solution. The two most common fixatives used are glutaraldehyde and paraformaldehyde. Samples are left in fixative from 2 to 24 hours. The tissue is then washed in buffer and placed in osmium tetroxide. A post-fixative, which is particularly useful for the preservation of cell membranes. Osmium tetroxide combines with lipids to produce black insoluble compounds. The tissue samples become blackened. The next steps are dehydration, where water is completely removed by using increasing concentrations of alcohol. Alcohol is then replaced with propylene oxide that is miscible with alcohol and epoxy resins. Specimens are infiltrated initially with resin diluted with propylene oxide and eventually with 100% fresh resin. After approximately 36 hours of resin infiltration, the tissue is ready for embedding. Each piece is placed into a small rubber mold and resin is added. The mold is then placed into a 60-degree oven for 2 days to harden the resin. The block is now ready for trimming and section cutting. Since the resin is very hard, sections can only be cut using glass or diamond knives. A glass knife is made from a strip of glass. First, a square is cut, then scored and fractured diagonally into 2 triangular glass knives. A daub of dental wax is placed just below the knife edge to hold a drop of water. As sections are cut, they float onto this water. Now that glass knives have been made, trimming and sectioning of the hardened resin block can start. First, the area of interest in the tissue sample is identified in survey sections. The cutting of the hardened block is trimmed into the shape of a trapezoid using a razor blade and a dissecting microscope. Final trimming is done using the precision controls of the ultramicrotome and a glass knife. When the full cutting face is exposed, a new knife is inserted into the ultramicrotome. The water bath filled with water and sections 0.5 microns in thickness are cut. These sections are called survey sections. They are transferred using a fine pipette tip onto a drop of toluidine blue stain on a microscope slide. The slide is dried on a hot plate and then viewed with a light microscope. Survey sections are examined with the light microscope to locate the area of interest and to check the orientation and preservation of the tissue. Note the trapezoid shape of the block. Cells and structures are coloured blue with the dye toluidine blue. This section also shows precipitation of the dye on the section. Survey sections are too large and too thick to use in the electron microscope. Hence the block is retrimmed to reduce the area of the cutting face. The retrimmed block is returned to the ultramicrotome and realigned. The glass knife is replaced with a diamond knife that makes cutting the ultra-thin sections easier. The water bath is filled with water and the ultra-thin sections float off as they leave the knife edge. The different colours of the sections result from interference between the rays of light reflected off the upper and lower surfaces of the sections. Colours vary according to thickness. Compression in the sections is removed by using chloroform vapour. Note the colour changes as the sections stretch out. The chart shows the thickness of the different coloured sections. Only the silver to gold coloured sections are suitable for electron microscopy. They are 70 to 90 nanometers thick. Sections are now ready to be collected onto a copper alloy support grid. The diameter of the grid is 3 millimeters, and it consists of a fine meshwork that supports the thin sections. Grids are used instead of glass slides because the electrons cannot penetrate glass. The grid is lowered into the water bath and the sections manoeuvred onto it. The grids with the sections on them are then dried on filter paper. The final step in tissue preparation is staining. Contrast in electron microscopy is enhanced using heavy metals, for example uranium and lead. Deposits of heavy metals in the sections deflect the electron beam. This area of the tissue will appear black in electron microscopy because no electrons have activated the emission of visible light from the fluorescent screen. These areas are referred to as being electron dense. Areas in the tissue lacking heavy metals allow electrons to pass through to the fluorescent screen, where they activate the emission of visible light. These areas are referred to as being electron light or electron lucent. To stain the sections, the grid is lowered onto a drop of uranyl acetate solution, washed, then stained with lead citrate. After washing, the sections are finally ready for viewing with the electron microscope. This is one of several transmission electron microscopes at Adelaide Microscopy, University of Adelaide. The grid is first placed into the specimen holder and then inserted into the electron microscope. The vacuum is restored. The section can be viewed either by looking at the fluorescent screen in the microscope or by viewing a monitor. At 1000 times magnification, the mesh of the grid and cellular outline can be seen. At 10,000 times magnification, the structural detail is very clear. At 25,000 times magnification, cytoplasmic details and membranes can be seen.